Those ones. All right, okay. So thanks everyone for coming along to the talk tonight. This is going to be quite a different talk because I'm actually presenting a poster, and the poster, of course, is up on the back wall as well. And the reason for doing a poster was because I gave this talk last year at EAG and another version of it at the first AGC event, and I realised that explaining a lot of the concepts in a presentation and not having the same type of having the right kind of examples wasn't kind of as useful in a 20-minute presentation context as it is to say stare at a big poster when there's lots of useful information to just sit there and stare at. But I'm now presenting the poster anyway as a technical talk because it seemed to be the right sort of idea at the time when people were scouting around for a talk to be had, and I'd just come from off a conference where I presented a lot of hopefully really interesting, useful examples of proof of concept. So I hope you'll enjoy this talk, and a couple of things to note on the title slide, and I'm just going to show just a couple of introductory slides that were taken from last year, and then I'll just go straight to the poster. That's the FVOS torsion balance, which is the instrument where the first gravity surveys were made back in the 1880s, 1890s perhaps. And the effects of what was measured by the torsion balance take effect inside this particular talk. And so getting from that to something like this, that's one of the stories of the talk. So some of you may have seen the parts of this talk or the talk itself last year, but I'm hoping that it'll be a bit more edified by having a lot better case study examples. A quick warning about the phone. And I just realised as well that my video and on my phone out upstairs, I forgot to turn off the press and mute button. So I hope I don't get any calls either. Okay, let me just go to the motivation for doing this talk, and basically it came from carrying out a lot of assessment and report writing for different clients in the oil and gas industry, but also from the minerals industry over the years. And I've worked primarily in the minerals industry in the past in potential fields, but I've moved more into the oil and gas sector over the last few years because there's been a higher demand for potential fields work, or at least in acquisition and then subsequent interpretation projects. That's expanded quite a lot in the oil and gas sector over the last sort of 8 or so years. And it's accelerated probably a bit over the last few years while the price of oil has been low, and they've been looking for non-seismic methods to help with a lot of the original exploration, which has been a great thing because it started to actually bring people back together from just focusing just on seismic data and actually integrating different types of seismic data products. But along the side of this has come this new realm of this area called gravity gradiometry, and one of the motivations for doing this talk, as I had mentioned, comes from doing a lot of the processing and interp and quality control of different types of AGG surveys, so the Falcon or full FGG surveys, looking at what products are being produced by the contractors and what's being delivered up to clients, and then understanding that, realizing that there's a gap between what happens when the contractors sometimes deliver a lot of the reports because they deliver products which, whilst they understand them and explain them fairly well, I guess, maybe at the time, the people, the non-seismic specialists, the mostly seismic specialists or petroleum geologists in particular, and then also in the case of minerals, gravity gradiometry, they don't often know what to do with a lot of the different products, and also understanding that some of the products that are being delivered don't always can convey a physical meaning. And I get concerned that there's a gap between the geophysicists acquiring the data and the end users, and this means that I worry about the value of the data after its delivery and the overall lack of application and understanding. So that leads to, of course, the generic concept of that the product is only as useful as the information inside it and how that information gets presented. So there's many different ways to present geophysical anomalies in maps, and It's very easy to get confused if things are not correctly labelled and you don't have physical meaning, you don't know what they are. And some of these kind of filters that get applied to magnetics data and gravity data don't necessarily really contain anything that's actually really proper physical information. And that, to me, sometimes, unless you really know what you're doing, it can very easily be misinterpreted by a lot of people. And this can be things like partial derivatives, for example, and integrals of transforms. Sometimes linear processing filters, different types of arbitrary depth slicing. Sometimes you can filter data any kind of way you want, but it doesn't really help if that product is only understood by the person who's made it. So let's go back to the question now of gravity gradiometry. Okay, that's what the focus of this particular talk. And this talk, which is entitled The Application, well, we're in a very big area, The Application of Gravitational Curvature Analysis to Structural Domain in Geology. It's really an interpretation talk. And there's been a lot of talks that have come in the last few years about modelling and inversion of data, and that's fine, but it's all, once again, it's only a great thing if you actually understand what you're actually modelling and interpreting in the first place, and the thing that you're actually modelling, you actually realise what it potentially might be before you actually go out and model it. So. But I need to talk specifically about interpretation, because I think this is really still where it all starts, and understanding gravity gradient data is actually a key to a lot of very interesting interpretation, and it's led me into some findings which may be hopefully really useful in future standard mapping type exercises. And what I want to explain to you is a little bit about gravity gradient data itself. Gravity gradient data is actually like a multi-channel data set. It's got five independent components in it, and they're explained over here in this figure. You've got, where's the pointer? Here's our gravity field. You've got a gravity potential, it's just the energy. And then you differentiate the energy, you get a force, and you get the changes in the force, which are changes in acceleration in the gravity gradient. This part here, the GZ, this is the part that is usually measured by standard ground surveys. You don't usually measure the X component or the Y component of the gravity field. They're usually far too weak to measure. The gravity field is a subtle enough thing to measure. But it turns out that the variations in the gravity gradients, this is like the GZZ, the first derivative of that, the first vertical derivative, and it's changes with respect to the Y direction and the X direction, and also the changes in the pure X components and the Y components of the field are actually quite strong, and you can measure these things quite reasonably with instruments that actually really resemble advanced versions of the EPOS, of the torsion darts, in the case of the Falcon system. But still, what happens is that in a gravity gradiometry survey, what happens is that there are 9 different components that are recorded in a gravity gradient survey. Only 5 of them are actually independent, with the GZ being equivalent to the sum of the XX and the YY components. That's called the Laplace equation. It's the consortium, another statement of the conservation management. And so you end up with, usually with a delivery of 6 different components. The GZZ, which is usually the most one-to-one and directly interpretable object, and these other items over here, which most people don't have a clue what they actually mean, and when they look at maps of them, they can't really figure out what they're supposed to be used for in interpretation. So normally when you go out and you interpret gravity data, what you would typically use is you would use this downward component, this GZ, the Buga gravity, the free air gravity offshore, or you might take a first vertical derivative of it, which is like this GZZ component. So they're the ones that are most usually used in interpretation and in modelling. But these other information, the other information of these parts here, are not really being utilised, and actually they can convey an awful lot of very important information. What's the next most relevant part of the talk? Okay, so the problem with these bits, right, is that these parts of the survey, they vary depending on which direction that you're acquiring the data. So if I'm flying along in my survey in this direction, and this is, each of these blobs and squares on the ground represents a geophysical, a geological object, and then I go in this direction, I'm going to see a different signal response. So my GXX in that direction compared to whereas if I flew my GXX if I flew the survey in that direction, it's going to look a bit different. Okay, so this is called a coordinate dependence. However, it turns out, so people, when you see these components delivered, the information that you see on these things is, except for the GZZ, relatively speaking, because that's what they call invariant, at least in the Z direction, because you're looking straight down an object, you can sitting everything as a sort of monopoles sitting in the ground. All the rest of it is going to vary. So depending on which way you measure it. So you can't really interpret those data as they are pretty much anyway. So you have to, but there is ways of utilising these data where the variance in these particular quantities doesn't actually vary. And that actually comes in the form of some things that most people actually already know about in the case of this thing, for example. This is the total horizontal gradient, or the total horizontal derivative. So when you do a total horizontal derivative in magnetics or in gravity, and you compute it from the vertical gravity or from TMI, what you're actually measuring is the sum of the squares of this bit and this bit. And it's a square root. It's always a positive quantity, but it doesn't matter if you fly the survey that way, or if you fly it that way, fly it this way. The effect of these gradients, the sum of these squares of these effects is always going to be the same. So this total horizontal gradient is what you call an invariant quantity. And it turns out as well that there's another invariant relationship which relates the XX and the YY, and this other funny little bugger here, the XY component. And it's called the total horizontal curvature. And it was actually this quantity that was actually being used by ECFOS back in the day as the thing that gets measured by the instrument. The value that gets measured is actually this difference between, by that torsionist, actually the difference between the X and the YY components. It's half the difference. Okay, so you've got one relationship which is just grouping those two things together, and then you've got another independent relationship which is talking about the variation between these two different components. And you can work out what the total horizontal curvature is, and that's actually the same expression as the total horizontal gradient. It's the sum of the squares of this UV, which is the grouping of these two bits, and the XY bit. So now you've got actually two ways of explaining gravity and variation in space, apart from in the vertical. You've now got two different ways of explaining the deviation that's being caused by a dense object in space, both in terms of its slope and in terms of the deflection of its curvature. So those two things are going to tell you about its geometry and tell you about the changing shape of the object. They're influenced strongly, of course, by density, but they're definitely very strongly influenced by geometry. So these three things, for example, are the only parts that are measured by a Falcon gravity gradiometry instrument. Okay? They use mathematical transformations, Fourier transformations, to get from these things back to this. Theoretically, if you have just one of these things, you can predict all the others, because if you assume things like the Laplace condition sort of hold the conditions, but you won't necessarily get best answers for estimates for these other bits, but you can predict them at least anyway. So they're predicting, for example, what this thing is, and they're predicting what this thing is based on those things. But they make up for the fact that, these signals are relatively weak by them making the instrument bigger. And so in the end, it turns out that FTG and other things are relatively similar. When you have an FTG instrument like the Bell or the British Forth systems, they measure all of these things, and so you get a specific measure of all these different things. But it doesn't really matter, because at least with both of those things, you can derive all these different bits and then use them usefully to hopefully get some interesting information about the data. So this is what I'm talking about here. So there's other things that you can derive from these horizontal gradients. So you've got two distinct types where you've actually where you explain the horizontal gradient variation independently within variance. You've got the horizontal gradient and the horizontal curvature. You can also use these things in a ratio with the vertical gradient, and these things explain the shape deviation of objects in 3D space. It's a phase relationship. So it's actually the ratio of the vertical component to this bit and the ratio of the vertical component to this bit. One of them many of you are potentially familiar with. It's called the tilt angle, and that came about in magnetics analysis, probably the beginning way back in the 90s, but didn't start coming into common use until probably the early to mid 2000s. And then there's this thing, which I've called the curvature angle, and I haven't invented this term. It was being also referred to as the shape index, and it was a guy called Carlos Savalas who sort of came up with this. He was at CDG before, and he had got this idea from optics. He'd come at this conclusion for the shape index from optics, where you're measuring the deflection and curvature of a lens. And so the way you measured it, whether it was flat or whether you're on a slope or on the edge or on a peak, it actually has got a relationship with gravity, which is the same. And it turns out that it's actually the same type of relationship as this thing. It's just the vertical gradient divided by the horizontal curvature expressed as an angle. He had it as a dimensionless thing from going from plus to minus 1. It actually makes more sense to think about it and analyse it exactly the same way as a tilt angle, because it's a phase angle between the vertical gradient and horizontal curvature. So I'm calling it the curvature angle. So these things now I've realised, once I had these things together, I've actually realised I've gone from 6 different ways of grouping a gravity gradient tensor down to 3. So I've got this bit and those bits here. Now, I thought that was a very interesting thing, and I'll come back and talk about eigenvalues in just a moment. But what I wanted to do was to make sense of some of these things, what they actually do, was to look at a 3D model and sort of try and understand the effects of what these particular components mean through 3D modeling. And so in this example, I've got a simple basement interface. It's just like you've got a imaginary sedimentary basin environment. You've got a basement interface, which is basically a bunch of valleys or basins in it and domes. There's sort of a saddle zone coming along here. Originally, I put some sort of small structures and fractures in there, but I didn't really put enough displacement on them in this particular model. But it's at a realistic sort of size. It's about 50 kilometres across that way, 5 kilometres in that extent. So you end up with a basement depth model that looks like this. This is the deepest part. Some shallow sort of depot centres there, if you like. Saddle zone coming along here, and some high bits along on this side of the model. So I was like, okay, I've got this sort of simple 3D model. I can forward calculate what all these different components of gravity gradient tensor are. And I hope that some of these things are clear enough. So this is a very simple model, so you get some pretty one-to-one looking answers. For the GZZ, of course, you're going to get the strongest gravity response where the higher density basement pops up. Where the lower density sediments accumulate, you're going to get the lowest response. So it's pretty simple and straightforward. But is it? If we only had that, will we know that that's what we were actually looking at? Or could these actually represent something else? And that is sort of the basic question about understanding what's in the gravity image. So how do I, if there's more information that I can get out of this, that actually helps me characterize what this interface system actually is, or this geological system actually is. Okay, so knowing that what the total horizontal gradient is, I can easily compute that, and you can see that I get the strongest anomalies on the slopes. So here's these are the slopes of the bodies. Over the saddle zones, total horizontal gradient goes to 0. That means the geometry of the object is flat, basically. So, but I get the strongest amounts of curvature of the strongest amounts of slope, if you like. Of course, in these areas. There, get the least amount of here, and that's what this thing essentially shows. But what about the total horizontal curvature? That's going to tell me something different. This is showing, the total horizontal curvature is showing, well, this is my steepest, sharpest looking anticline, so most severe shape of it. I'm getting a maximum response over that object. I'm also getting a bit of a significant response over this saddle zone as well. Because this has actually got, I've actually got curvature coming over the saddle. It's flat on the top, it's curving over the sides. So that's curved too. This is also strongly curved, but down the bottom here, in the bottom of the basement trough, I don't actually have as much curvature. So that's actually quite a significant thing to consider. So this is telling you about the variation in the shape as well as the variation in the slope. Okay, so, but what happens when I so that's given me a couple of other different interesting ways of characterizing the geological information in an image, just by understanding what these things actually kind of mean with respect to a simple model. I start to understand what the anomalies are actually representing geometrically.
So is that maximum curvature you're looking at basically there, rather than?
Yeah, so this is like maximum curvature. Maximum curvature is occurring where the basement is the most curving. See, this is the highest amount of curvature here and here, up in this corner, where these things are, and where these objects are the most curved. So there's the least amount of curvature occurring over these bits in general, and sometimes also down the bottom.
Some of the curvature, just looking at some of the curvature is east-west and some of it is north-south.
That's right,
It's a combination.
It's a combination effect, yeah. Yeah, that's right. Just looking at the, compare the curvature angle and the tilt angle. In this simple example, they actually converge to something that looks mostly similar because the GZZ signal is pretty dominant. The tilt angle, these are both phases that run from -90 to ±90. So over something that's dominantly vertical in nature, you're going to get a simple maximum over the top of a tilted over a vertical body that's at 90 degrees. What will actually happen in the curvature angle is that you tend to get the maxima closest to the edges, and then it'll flatten out over the top, which is what you get in these things. Even though they look superficially similar, you can see it's flattening out. It gets pretty high there, and then it flattens out over the top. But it's showing the edges of the slopes extremely well. Both of them are in this instance. But where they deviate strongly will be due to the gross, well, some basically basically just a combination of density contrasts and changes in the gross overall geometrical patterns. So if these things diverge considerably from one another, then that's actually telling you about some nature of the morphology of the geological contrasts at depth. Okay, these things are different. Okay, so that's fine. That's all very interesting, but I just want to digress into another area, and this is a little bit more complicated. I'll just show the text first. There's some more information that's actually present inside the gravity gradient tensor. And I've talked about this coordinate dependence, and it turns out when you've got, because these tensors are symmetric, you can decompose these tensors into using a process called diagonalization. It's the same as doing linear algebra on a 3x3 matrix. And to produce a form where all of the signal of the tensor is now contained only in 3 components. So instead of having all of these and representing all the variations in the signal, if you flew it in the most perfect coordination and with the maximum coupling, all the signal would be contained just in these 3 bits, an XX, a Y, and a ZZ. And this is a process called diagonalization. And you would produce these values here, which kind of are a little bit like, they vary a little bit like the way these things vary. They're called the eigenvalues of the system. And most of you probably familiar with what eigenvalues mean. And this is the equation for the diagonalization of this matrix. When you solve this matrix, or when you solve this matrix equation, you involve a tensor determinant, so the determinant of a matrix. And you get this equation here, which involves the determinant of the tensor, the eigenvalues, and the identity matrix. You solve this to get the characteristic equation for the tensor, and then you realize that you have several different elements involving cubes and squares and linear parts and a thesis shift. Now, when you solve for this, you discover that the first part, these different numerical factors here, I naught. This is actually the in this component here. This is actually the trace. It's the same as this. This is the trace of the tensor, and it's also the sum of these things, and the sum of these things should be 0. Then you have 2 other bits. They're called I1 and I2. Turns out I1 is just the sum of the squares of this thing, which looks a bit like one of these. And in fact it is. But instead of using just those components, or those components, you're now using all of these things rotated all represented as signal maxima through principal components. So this would come out, if you summed all these things up, it would come out as n squared. So you take the square root of it, and you've basically got an analytic signal. So it's the same as an analytic signal. This is like a 2D analytic signal. This is like a 3D analytic signal. You stick a square root in front of it, and you get back to 2 n plus, or milligauss to -1, or milligauss per meter. The other thing that comes out is this I2 part here is a determinant. This is just the determinant of the 3x3 matrix, okay, and that's actually the product of these things. So one's a sum of squares, one's a product. Okay, so you have here it's an analytic signal, the eigenvalue analytic signal, and it's the same as an analytic signal. When you do an analytic signal of magnetics data, you're actually only using these things. When you're doing an analytic signal of tensor, you're using all of it. So you're getting the full tensor signal. So it's actually like a bit of an envelope function. It's measuring the maximum signal variation of the tensor. And it's always a positive quantity, whether the mass contrast is positive or the mass contrast is negative. This determinant is a cube root, so it's going to have a positive side and a negative side. It's going to have a bimodal distribution. These all have physical meanings. Here's an example of what the analytic signal represents. The biggest contribution of gravity signal in this actually comes from the sedimentary trough, because that's got the that's got the biggest size, it's got the most contrast of the basement and the basement. So you get the biggest signal out there. Same with out in this area, you get quite a big signal contribution here. You also get a big signal contribution up in this area where the basement is high. The basement's coming closer, that's a very, very big positive contrast. This is a very big negative contrast, but you're seeing it as a positive because it's a square. Where the analytic signal goes to 0, once again, there's no change going on, relatively speaking. So it's, you're dealing with something that's flat. Cube depth. So that is the same as this is the sum of squares. This is a product. So this is FOS cubed. You cube it, and it's the cube of the determinant. What's the cube of the determinant most sensitive to? The determinant is actually most sensitive to changes in mass per unit volume. So you're getting variations in the mass changes that are occurring inside a geological area when you look at a changing determinant. You'll get the strongest in changes in mass, where the strongest changes in mass, of course, are high. And that is often the saddle zone. This is although this is a flat, this is actually an area of uplifted basement. There's a positive mass contribution here. There's a negative mass contribution here. So at least by comparing this one and this one, I can differentiate which part of the system I'm actually in. Okay? Because I'm saying this is all positive here, but it's actually negative on this one. Ah, that means it's a mass loss. I must be in the basic environment. That's how I'm distinguishing what's actually my signals actually representing. So, it's one way of us saying that it can't be something else. So you've now got. It turns out that this particular factor here is very sensitive to fracturing and destruction of mass. So changes in mass. So where there's faulting and fault zones, you tend to get destruction of the degradation of the determinant. Also, where this value is closer to 0, you've essentially got two-dimensional geology. I want to go back to, so that's another product that can come out. I want to go back to one more thing a couple of other things before I go to show some real examples. Just go back to this concept of three-way grouping. I used to do a lot of interpretation of Landsat data, and that's usually comes in as a multi-band grid, seven channels in it, and then we will use some of the channels to combine together to represent different things. The first time I ever loaded up a tensor grid, which is from in the Intrepid format, it comes as a 6-band grid. And the first thing, of course, EMAPA tries to do is load it up as an RGB. But then I could never get any of the combinations to work, and I didn't know at the time because I was having this problem that all the different bits, the x's and the xy's and all that, they're all subject to variation. So they're never gonna make that much sense when you combine them with something else. But what does make sense, of course, I realised was actually using these two things. Maybe you could try them together and actually see what happens when you use the bits that don't vary and you put them into a 3-band image. Because you've only gone back to three different things. And so when you try that, you end up with this. This is just a 3-band color image showing you the red part that comes from the GZZ. It's natural to put that as red. The green coming from the THC. The blue coming from the total horizontal grading. And now you can see that I've got maximum blue, where I've got the steepest slopes. I've got maximum, kind of a combination of all of these things, where I've got right on the crest of an anticline. Dominantly green usually, where I'm down in the bottom of the basement or in a syncline. I usually get a simple red colour when I'm dealing with most probably uplifted basement and uplifted positive density contrast, but weaker geometrical contrasts. So flat type geology. And I was like, wow, this is pretty cool. It looks pretty, but what does it actually, am I actually definitely seeing this kind of stuff all the time whenever I combine these things together? I decided to try some other tricks as well. I'm very fond of using intensity bands as well when doing image contrast instead of using a sunshade. The analytic signal is a particularly good thing to use as an intensity band, so that's where the colour varies according to one signal, but the brightness or darkness of the signal varies according to something else. And so it actually makes sense to use something that describes the variation in the signal strength of the geology as an intensity band. And so you put that in as the intensity band, it's this one, and I discovered that all my saddle zones show up as black spots. But I still get this amazing differentiation of colour telling me which parts of the basin I'm actually in. And then that made me think, well, this is actually the same as if you're in a geological map. So if you're in a geological map, and these are all different rocks, you can have this exactly the same expression just by putting a lower density sediment here, a lower density sediment here, a higher density sediment here. So that means I'm probably differentiating geology as well. What about if I try something like the cube root of the determinant, because that's sensitive to changes in mass. I put that in as an intensity band instead. And what do I get? Here, instead of having these black zones, I get red zones. These are telling me definitively that these things, what these different parts, ambiguous parts of the geology will probably mean. It's telling me that these are most definitely highs, and this is most definitely a basement low. This is most definitely a saddle. So I'm like, okay, all right, fine. And that's all I basically had at the presentations last year. I'm like, well, where's my proof of concept? And I have to go to a real-world examples, and I wanted to use this Brewer Energy one because originally this was for on a gas poster, but this, the problem is that the ground geology just simply wasn't very well mapped. Of course, out here you're in the Canning Basin, and it's all sand. So I decided to use this other publicly available ADG survey, Falcon survey. It was up in the Halls Creek origin. So this is 500 metre line space data, and the survey is about 50 kilometres wide by about 140 kilometres in length. And so I reprocessed that and sharpened up the images, and I just want to show you just take you through some examples. So I've sort of just taken the original geology from the Geological Survey, just the polygons, from mapped at 100,000 scale. And here we've got metamorphic rocks, we've got some tonalites in there, we've got different types of granite, there's some siltstones out on the margins, we've also got gabbros and in here, different types of gabbros in there, and we've also got some zones of ultramafics and metamorphics. On the edge of the area we've got some sandstones as well. So I've just broadly grouped them together according to the major rock types, and there's a couple of profiles that were in the original 250,000 scale mapping, which I've just put a couple of profile lines on. So later. Now, so you've got a GZZ signal, and the GZZ says fine. Okay, I've got some dense stuff here maybe, and some lower density stuff here, some higher density stuff here, and different stuff here. And also got lots of interesting structural fabrics as well. But what do they all mean? I don't know what they mean. That could be anything. This still doesn't tell me everything, right? But what do they mean? Let's have a look at one of the other transforms. Here's a tilt angle. Tilt angle is fairly similar to the GZZ, but it also shows the continuity of the geology and the structure a lot more sharply than the GZZ on its own. But it's going to be fairly similar because we're dealing with stuff that's fairly close to surface with strongly metamorphic igneous geology content. Although it's different, obviously it's different in this area. I decided to also just throw some 100,000 scale interpreted structures from the Geological Survey as well that they've done before, probably mostly based on either field mapping or probably aeromag interpretation. And look, throw that on top of, actually, well, this is in fact the curvature angle. But you can see it also as well with the tilt angle, because the curvature angle is showing me not just the edges of the units here, but a lot of beautiful cross-cutting structures as well, due to the rough changing contrast of the rocks in the near surface. But you can see the original structural lineament mapping is not bad. You can see there's probably some errors in it too. Picking up many of the same types of things, but actually the ASEG side is probably picking up anything. It's probably picking up a lot more. So that's wonderful enough. Okay, so that's fine. So what about these RGB type images? Are they actually telling me anything useful? So here we have attempted throwing these things into combination, and now to validate it, what I do is just drop the polygons on from the Geological Survey mapping and see if they actually start to differentiate, if the variations in this actually line up with the differentiation in the geology. And to my great relief, actually they do. So, bearing in mind, that's probably much of the interpretation sources, so it's probably still some air photo. There's going to be differences between what the gravity sees and what other different interpretation stuff produces. I think it's, for just simply dropping on a polygon data set, I'm doing a pretty remarkable job of defining a lot of the principal units. In fact, even to the point of differentiating different types of ground. That's with the, this combination I'm using here has the analytic signal intensity on the bottom. If I want to use the cube depth intensity on the bottom, then I get a variation on this image. The RGB pattern is still the same, but now the contrast in the image just is telling me a different story again about the nature of the geology. Even as simple as this, that's a different unit. This thing. There's not much. There wouldn't be anything on the GZZ much to tell you that this is different from that. But this type of image does.
Wait, let's see that GZZ again. Hot damn.
And so, even down the side here where the sedimentary units start encroaching upon the edge, it's quite beautifully defined in both of these data sets.
What about some of the structure?
These are actually different types of remnant units, and they look different.
Can we see the structure you showed in the upper right?
Yeah.
Oh, what I prepared.
So that's the structure. So you could probably argue that, there's a lot of similarity and there's some differences. But then you would then go and, of course, go through a process of refinement. I mean, I hate to add to the interpreter's job of complexity, just reconciling things that are similar and different, but here you now, looks like you have another one. So that's pretty much it. Like, it's still early days for this kind of thing, and you can also, probably better to do this on in the posters, but I included these cross sections as well. The length of these cross sections, you can basically just do, just eyeball off different sections of this along these different cross sections, and yeah, just relate the, like, for example, this one is the southern one. That thing is this thing is this is in the contrast across the middle here. This thing is something else. Blah blah blah. So actually it might be the other way around. This is the density, which is that thing. Yeah, so yeah, you can basically line these things up, and I didn't have time to. This just came off from 250,000 scale geology. I put it on there just for people to find pin bits of it down themselves. I could have bracketed it all off, I suppose. But that's it. So I guess the take-home points are really about trying to utilize the data, and the fact that these bits here are just as useful as this bit, but you need the right way and right environment in which to actually present that information. And you can do it, the best ways as usual of doing it is either, at least as far as these are concerned, is by producing these two products, and that's making best use of that information in one respect, and then the other respect is computing those things but putting them into those RGB images, and then that will help you separate and differentiate either geometry or geology. If you're close to the source, you're going to be density dominated. If you're in a sedimentary basin environment, you're going to be geometry dominated, and localized, positive effects will tend to stand out, like if you're on carbonates or volcanoes or things like that. So will tend to stand out as bright yellow spots or red spots, for example. So that's pretty much. I mean, that's just a conceptual sort of understanding of how gravity sort of behaves. I mean, obviously, there's probably going to be some similarities. So I've tried it with magnetic data as well, but there's not at the moment. I mean, you can derive these things theoretically from magnetics, but probably helps to have actually gone out and got some squid mag tensor data or something like that. Try some of those things with that. But yeah, you do get some pretty interesting results with mag as well. It's probably another discussion about using invariance and determinants and things like that, when you're talking about something that's a dot that has essentially dipole events. So that's probably a bit of another subject for another discussion at some point. Another thing that's of interest, and I didn't mention, is that this tilt angle is related to the depth. So the 45-degree contours, these aren't 45-degree contours, but where you're going from, roughly around about there, from 0 to 45 is similar to the depth to the object, of the vertical object. But it's not perfect, it's only if the object's vertical. If you use the curvature angle, it's telling you about the shape deviation. So the curvature angle must be, you must be able to use those two together in some ways to help modify depth equations. Yeah, so that's it. So yeah, thanks all for listening. It's still early days for this kind of stuff, but it's something I've been working on and off for 2 or 3 years now.
Anthony, sensational. Sensational, but a trivial observation. Can you go to the top?
Yeah.
Top,
Which place?
the starting point of that is a depth image at an interface, right? With
Yeah.
with a density value above or below of 2.4.
2.4 and 2.67. I think I left the basement density off.
Just trivially, it would look
Yeah.
fabulous to have all those other little images draped in 3D. And the same with your second poster. I mean,
Sure.
it would be fantastic. And instead of Z, maybe GZ is the vertical axis.
Something like that, yeah. So, you're completely right. Like, some of these images, like these kinds of things, give you, especially the intensity image on the back, give you like a pseudo, especially in mag, you notice that very well in mag, but in mag, in Gravity 2, give you that already a pseudo 3D impression. Like when you look at a magnetics image, you'll see everything fade to dark, basically as you're heading off the edge of a metamorphic platform into a basin. And then you see the signals kind of, in a tilt angle kind of, sort of spread out, as you get deeper, as you get further away from the source, that kind of thing. You already get that pseudo 3D kind of impression, so the idea of actually displaying some of the stuff in 3D is pretty useful. The other thing I didn't mention was that this kind of idea, not just related to landscape stuff, it's also related to seismic, because they even do this stuff in seismic. It's called spectral decomposition. They do it with seismic color blending. So they just choose different sort of frequency bands that are sensitive to different seismic attributes, and they blend them also in colours to show variation in the shapes of the geology. So this thing is actually pretty much analogous. All you have to do is you have to just simply represent that by a simple density contrast in a layer, and you'll get a frequency contrast in the velocity model, which you can colour blend in the same way. Yeah. So, yeah. So I think there's things like that. So there's relationships and things like that as well.
Do you have any more questions?
Feels like cubed roots are pretty noisy.
Yeah. Anything that's a gradient is pretty noisy.
Anything with a gradient feels pretty noisy.
Yeah, anything with a gradient is pretty noisy. This has a bimodal distribution. It's like that. What it is. This is obviously it's a single-sided distribution starting from 0. But yeah, you can get a lot of noise in there. You quite often a lot of the signal, sometimes the curvature things are overemphasized by bad gridding, and by normal. They're also overemphasized by not, obviously sensitivity to terrain and changes and terrain processing and all the other horrible effects that affect potential field data processing. So they can carry through and contaminate the stuff. It's often a good idea to apply some sort of maybe some low pass filtering to the data, maybe